Okay. Okay, let us start this session. I'm Dejan Milošević, and the first speaker is Marc Vrakking. So he will talk about control of ion photoelectron entanglement in an attosecond experiment. So half an hour.
Yes. Okay, thank you. Yeah, so of course, I already talked to you to some extent about this theme 2 nights ago, and I think most of you were there at the time. So it basically means that at the beginning of my talk, I'm going to just remind you of a few things that I discussed the other day, but I'll go through very quickly because I'm assuming that the reminder is called that. Okay, so of course yes. So of course, the key point that I've tried to get across 2 nights ago was the idea that in attosecond science, we have to be very careful because we often, most of the time, in fact, study ionization processes, and in ionization processes, there's a very significant risk of performing an entangled system, of creating an entangled system. In other words, creating a situation where we have a wave function that cannot be written as a single direct product of ion for the electron wave function, but rather where we have a superposition of a whole bunch of these direct products. And what I've tried to emphasize is that this really has consequences for what we see in our experiment. The picture that we have arrived at 2 nights ago is basically that we can have a situation where the photoelectron can act as a kind of detector that can distinguish the ionic states that we form in the experiment. When that is the case, this will go at the expense of the ionic coherence that we can see. On the other hand, if we have situations where the photoelectrons cannot distinguish the ionic states, then nothing stands in the way of seeing ionic coherence. And what I'm going to show you today are a couple of experiments where we're able to switch back and forth between these 2 situations. Now, what I'm going to talk to you about is a little bit more about this vibrational experiment that I already explained the other night. There, in particular, what I'm going to talk about are some quantitative measures of the entanglement that we can extract from the computation of this experiment. And then I'm also going to talk to you about new experiments that we have done, where we basically have looked at the role of entanglement in experiments of electronic rather than vibration. Okay, so short reminder about the experimental setup. As I told you, we have this classic attosecond setup, shorts like sapphire laser balls coming in, being split, harmonic generation, and one arm, then a bunch of detection at the end. And of course, what I've explained is that the special feature of the instrument that we now use is that in the arm of the interferometer where we perform the harmonic generation, where we generate the attosecond pulses, we have integrated another interferometer, and with that interferometer, we take a pair of phase-locked IR pulses, which in the harmonic generation process leads to the generation of a pair of phase-locked action B pulses. And that we achieve this situation, we can, for example, see from the measurement of the harmonic spectrum where we have this pretty structure. The other night, I got a question about how we actually do this and how we keep this interferometer stable. So I want to show you a few results on this. So the interferometer, this one here, is both passively and actively stabilized. It's passively stabilized in the sense that it's small and heavy and well shielded. That basically gives good short-term stability, but you see that when we operate this interferometer over a period of something like half an hour or so, then the delay between the 2 IR pulses, the delay between the opposite pulses actually flips away a little bit. Therefore, we also have an active stabilization. We have a CW laser co-propagate along the same path, and we use the CW laser to create the interference pattern and we lock on that interference pattern. And the moment that we do that, the time delay really stays locked in place. There's also a very small jitter, below 10th of a second. In this situation, we can essentially go as long as we want. We run experiments with more than 24 hours. What I want to show you here is an experiment that we have used to characterize this interferometer and to convince us that it's really suitable for our experiment. And that's actually a very simple experiment where we've taken the helium atom and we've used the action B pulse pair to excite Rydberg states of the helium atom. In this particular case, we're really just interested in monitoring the evolution of the population of these Rydberg states as a function of action B delay. So the way that we've done the experiment is that a long time after the action B pulse pair, so a long time meaning hundreds of picoseconds or so, we've come in with a narrow band IR pulse. So basically put our femtosecond IR pulse through a narrow band interference filter. And we've used this IR pulse to basically depopulate these Rydberg states, create photoelectrons, and of course, every Rydberg state that we use to compare is the photoelectron. Yes, so this is the data set that we have created. So we measured the angle integrated photoelectron intensity, which also beta parameters describing the angular distribution of the photoelectrons as a function of the momentum of the photoelectrons and as a function of the delay between the two XUV pulses. Of course, we get a Fourier transform, go into the frequency domain, then we get sharp contributions corresponding to the contributions of individual Rydberg states. Now, these we can compare, and so this basically gives us line positions, transition frequencies for these Rydberg states that we can compare to values from the literature, and you basically see that they can reach submedical levels. That's simply restricted by how long we made the scan. In principle, there's no limit on how accurate we can do this, but this was good enough for our purposes. At the moment, we're extending these experiments. There's also some discussions that we had with Yoshi Reda, who visited us at MEI for a few months. And right now, the experiment is ongoing. I was hoping to show you a result, but the laser was a little bit friendly in the last few weeks. We're repeating the experiment, but now with a short pulse probe in the experiment. And that basically means that we're beating out the coherence between the things that we have here. Otherwise, the experiment is just going to Now, in the absence of experimental data, I can show you numerical data because we have done calculation of this experiment. And what we're hoping to measure are 2D maps like this, where on one hand we can have the frequency axis related to the XUV delay. That basically tells us about which XUV frequencies are absorbed. And the other experiment that are probed in the probe experiment. And so, of course, this is the alien symbol we extended. It's really very interesting to be discovered in it. And we think that this is a way to move attosecond science really in the direction of multidimensional spectroscopy. And we think that that is going to be very powerful. Interestingly, we do already see seeing a coherence between two different frequencies. And likewise, the excitation is too sweetly, then you can start corresponding, see correspondingly quality to 4K. But there also are peaks that do not follow this simple scheme. And that is actually the holography that we also briefly saw in one of the talks yesterday. But that's basically a situation where, on the one hand, we have the XUV directly ionizing the atom by means of the single photon. But also we have the XUV exciting Rydberg state, which is then ionized by the IR in a two-photon process at a variable time delay. Also, such components leave a well-defined signature in these two new maps. So like I said, this is what we're hoping to see in the laboratory. Okay, so let's return to the hydrogen experiments and remind you that what we did is basically ionized hydrogen using the pair of XUV pulses. In this case, the XUV pulses are short attosecond pulse rate. We did not make the effort in this case to use isolated attosecond pulses. And so we have XUV pulses, each about 5 femtoseconds long, ionize the H2, and as I explained the other night, that produces a vibrational wave packet, and we probe this vibrational wave packet at the counter turning point by time delay dissociation. That produces the H plus. We measure this H plus using what was and so the end result, as I explained, is basically that we get the angle integrated signal of the H plus, as well as a few angular parameters as a function of the velocity of the H plus, as a function of the delay between the two XUV modes, and a function of the XUV IR and the delay. So this data I showed before, the remarkable thing, of course, was the fact that one of these that we show that we see in the experiment very strongly depends on the XUV delay, as in particular these nearest neighbor quantities very strongly for a delay of 29 femtoseconds
and not so much for a delay of 45. So all the data is then compiled in this plot, right, where you see that the intensity of all these Fourier components has so 4 different quantum beats, both the angle integrated signal as well as the angular parameters. Everything oscillates as a function of XUV delay with a period that is inversely proportional to the energy difference between the 2 states that are involved. Okay, and then what I've promised you is to explain how this is related to quantum mechanical entanglement. I already showed you this simple way to think about the experiment, basically to consider the consequences of the fact that in an XUV pulse pair, we have a fringe structure for a delay of 2 pi divided by the energy difference. This fringe structure basically matches the energy difference between the 2 vibrational states that we're considering. So that basically means that there a possible measurement of the photoelectron really doesn't help us to distinguish the ionic state. In other words, there we have a separable system and the system is not entangled. On the other hand, at a delay like this, half as long, where the fringe spacing is twice as large, there a possible measurement of the photoelectron would really allow us to tell us which vibrational state we're dealing with. In other words, there we have an entangled system. And of course, the important thing is, the only thing that matters is that we are able to do this photoelectron measurement in principle. We're not actually compelled to do it in the laboratory. It suffices that it's possible in principle. Okay, so what I now want to show you is how we've also done this experiment as a numerical experiment. So there what I've done is basically propagate the time-dependent Schrödinger equation on a 2D grid, basically using 1 degree of freedom for the photoelectron and 1 degree of freedom for the internuclear motion. The other electron is considered bound, leading to electronic state 1 is sigma t or 2p sigma u. And that's in that sense done in the Born-Oppenheimer approximation. Now, then what I've calculated is really exactly what we do in the laboratory, or try to get as close as possible to it, in the sense that what I've calculated is the joint momentum spectrum of the photoelectrons produced by the XUV pulse and the momentum of the fragment ions. And this is done using the time-dependent surface flux method. And here, it's wonderful that Lars is in the audience. I don't see him. Where is he? There's Lars. I mean, the fact that this was possible, I really owe to Lars because he wrote an absolutely wonderful paper explaining in detail how one does such a calculation. So I used the first lockdown during Corona to learn how to do this. And yeah, that was a very enjoyable time. Okay, so the end result of a calculation is then basically one of these joint momentum distributions, as you see it here in the corner. And so this is basically a probability distribution that describes the probability to find the photoelectron with a certain momentum in combination with the H plus with a certain momentum. That's the end result of the calculation. Of course, there's some laser parameters that goes in. Suffice to say, this is all close to what we did experimentally. Okay, so now let's look at this a little bit more closely. So here again, I show you one of these joint momentum distributions. In this particular case, for a delay between the XUV pulses of 500 atomic units and a relatively long IR delay, I forget what it was. Qualitatively, we see a few things here that make sense. On the one hand, we see a fringe structure along the photoelectron momentum direction. That is simply a reflection of the fact that we have a fringe structure in our XUV spectrum that simply gets imprinted on the photoelectron. In the H plus momentum distributions, we don't see anything spectacular. And that is simply a consequence of the fact that this dissociation process that we use to detect is a very simple process, doesn't imprint any structure on the wave packet. There we are. Okay, so now what we want to do is see how this object behaves as a function of the other time delay that we have in the experiment, the XUV IR time delay. In order to plot this, since anyway there's not much happening in the H plus momentum direction, we're going to pick an H plus momentum here in the middle, and we're going to plot the momentum distribution as a function of photoelectron momentum and as a function of the second time delay. In this case, actually, the probe laser was a UV laser. That's why it's called XUV UV delay here. Okay, so that leads to this nice looking carpet that, of course, again, we treat by means of Fourier transformation. And that is then basically where, again, we see, just like in the experiment, that all the time-dependent behavior that we see here is explained by a finite number of quantum beats. At the same time, here we already begin to get the first indication that entanglement plays a role, in the sense that you see that the observability of certain quantum beats actually depends on the photoelectron momentum, the accompanying photoelectron momentum. And so if you pick one of them, you can see this component for a certain photoelectron momentum, not for other photoelectron momentum. Now, of course, in the experiment, we've never even measured these photoelectrons. So now we're going to do something that gets us a little bit closer to the experiment. In the lab, it also sometimes gets dark. Not as often as here, though. Well, let me say it in words. We're going to integrate over the photoelectron momentum, because in the lab, we only measure the H+ momentum distribution. So that's also what we're going to do here. Let's get checked in cooperates. And that basically means that the next slide that you will see in a moment will be a plot of the intensity of these different quantum beats integrated over photoelectron momentum, but now as a function of the XUV delay. And as you see, just like in the experiment, now we really need the slide. Okay. Okay. I can describe it in words. As you might see on the screen, is that just like in the experiment, the intensity of these different frequency components is oscillating as a function of XUV delay. So in that sense, we see an observation here in the numerical experiment that is very, very similar to the observation that we've made in the experiment. Okay, so far so good. We've done an experiment and we have done some numerics, and with the numerics, we reproduce the experiment. But now, of course, one thing that's very nice in the numerical experiment is that after the pump step of the experiment, so we're going to forget about the probing now, after the pump step, we have the wave function available on a grid. And it basically means that now we can start to analyze this wave function and see whether we can recognize the degree of entanglement in the wave function, in a sense that's not so different from what Francois showed you yesterday. Okay, so that basically means that there we go to the density matrix, the reduced density matrix, and we start to calculate properties that characterize the entanglement. For example, we can calculate the purity, which is a measure of the degree of entanglement. We can actually physically look at the reduced ionic density matrix. We'll be able to recognize coherence in there. And in a moment, you'll also see the Schmidt decomposition. That will also be a useful way to look at the entanglement. So in words, I've now described the rest of my talk to you. One thing we can calculate, for example, on the basis of our wave function is the purity of the wave function as a function of XUV delay. So that's actually what's plotted here. And there you see, we see the exact same oscillations that we've seen in the observability of the different Fourier components. Now, and of course, one thing that's now nice to do is that we can look on this curve and on different delays. And then, for example, take a look at what does the reduced ionic density matrix look like. And here, for example, this is in one of these valleys here where the purity is very, very low. In other words, where we have a system that's very much entangled, where we don't have a large degree of vibrational coherence. I mean, that's really borne out by the reduced ionic density matrix that we have, where basically, if you're sitting close enough, you can see that the matrix or the components directly next to the diagonal. So basically the coherences between adjacent vibrational levels, they're completely absent, right? And that's because, well, I mean, these two, there is no coherence between the two because the system is entangled. And then by contrast, for example, we can go to one of these delays where the purity is very high. Now, that's also immediately borne out by the reduced ionic density matrix, in the sense that now, if you look at the reduced ionic density matrix, you see that these components are very, very prominently there. Okay, what I found perhaps even more interesting and even more insightful to do is actually exactly what Francois told us yesterday, is to do a Schmidt decomposition. So here you basically see the results of a Schmidt decomposition at these two same delays. And what I'm plotting here is basically the ionic parts of the wave function for the different Schmidt components that we find. So I haven't plotted the electron part, I'm just looking at the ionic part. Now, and that actually shows something very interesting in the sense that if we now start with this case where we had a high purity, I mean, that's basically borne out by the Schmidt decomposition in the sense that we see that in this particular case, more than 96% of the wave function is accounted for by a single Schmidt component, right? So this basically means here a single direct product is a very good description of our wave. Ah, it's back. Excellent. A single direct product is a very good description of our wave function. And if we look at, what does this wave function look like? What does the ionic wave function look like in this case? See that basically it's a vibrational wave packet containing all of the vibrational states that the H2 plus has. By contrast, if we go to this valley in the purity, the case here where there is no coherence between adjacent vibrational states, then again, we can do the Schmidt decomposition. We see that now there are two Schmidt components that have almost equal weights. Together, they account for everything, but both of them carries about half of the weight. And interestingly, here we see that we have one vibrational wave packet that contains more or less all the odd vibrational states and another wave packet that contains all the even vibrational states. And of course, as a result of that, there is no coherence between the even and the odd. Okay, so that all makes a lot of sense. Okay, so what I now would like to do is then turn to the other experiment that we've done. It's an experiment with a minor modification in the experimental setup, but I think the experimentalists here will appreciate how big that modification in fact is, in the sense that the change that we've now made is that instead of ionizing H2 by a pair of short attosecond pulse strains, we are now ionizing the H2 by a pair of isolated attosecond pulses with a variable delay between them. And that is something that sounds a lot easier than it actually is. That really requires a lot of hard work to really make sure that the driver laser pulses are these 3.4 femtoseconds. And it also requires a lot of hard work to make sure that the laser is working well as a CP stable system. But that was accomplished. And with that, we're basically able to repeat more or less this experiment. So again, we're going to ionize the H2. We're going to let the H2 interact with an IR at a variable time delay. And again, we're going to measure the H plus that is coming out. Now, in this experiment, what we're interested in is electronic coherence. So we basically have to ask ourselves the question, is there an observable that we can measure that actually tells us about the electronic coherence that we have in the system? Unfortunately, there is, in a sense that in the dissociation of H2 plus, we can look at something that we call electron localization. Where electron localization basically means that if I look at the direction of ejection of the H plus, or conversely, if I ask myself the question, which direction is the neutral H atom flying, that in the laboratory frame, there can be a preferential direction for this. I can have situations where there's, for example, more H pluses flying towards the right than towards the left. And as I'll show you in a moment, that is an indicator that we have electronic coherence in the system. Now, the fact that this is so is very easy to see in the sense that, I mean, what we need for our description are just the two lowest electronic states of the H2 plus. And a little bit schematically, we can write these wave functions as a superposition of an electron wave function centered around the left proton or centered around the right proton, where the ground state basically has a wave function where we have this superposition with a plus sign. That basically means that there's a lot of electron density between the two atoms. That's why it's a bound state. This excited state is a superposition with a minus sign. There's a node in the wave function between the two atoms. That's why it's a repulsive state. Now this we can rewrite a little bit, and then we can see what it means for us to find the electron on the left or on the right side of the atom. It basically means that one way or another, we have put the atom into a coherent superposition of the gerade and the ungerade state. And that is why I'm saying that this electron localization is a nice measure of the existence of this electronic coherence between the gerade and ungerade component. Important to realize is that in ionization, we produce a wave function that we can schematically write like this. We can either form the ground state of the molecular ion in combination with a photoelectron that has odd angular momentum, or we can form this first excited state of the ion in combination with a photoelectron that has even angular momentum. So I think you recognize this is an entangled wave function. There is no electronic coherence in this. And so that basically means that in this pump probe experiment, the electronic coherence needs to be created by the IR laser. the XUV produces zero electronic coherence. Now that this is possible is of course something that we know from a number of years ago. This is a result that Fernando also showed on Monday, a project that we already collaborated on many years ago. So this was an experiment that we did in the laboratory of Mauro Nisoli in Milano, where in fact we saw that it is possible to measure this electron localization. Here you basically see the asymmetry in the number of H pluses flying up versus the number of H plus ions flying down as a function of the kinetic energy of these H pluses and as a function of the delay between an isolated attosecond pulse that initiated the experiment and a few cycle IR pulse that did the cloning. And so now what we're going to do is basically repeat this experiment and replace the isolated attosecond pulse by a pair of isolated attosecond pulses with a variable delay. So this is the new data set that we have reported. As you see, it's the same kind of experiment, but now for many different delays between this attosecond pulse pair. What I'm showing you here is more or less the raw data. We're still working on the manuscript and plotting it up in a nicer way. But already from the raw data, you can see something very essential. There are certain delays between the XUV pulses. For example, this delay of 6 femtoseconds or this delay of 9 femtoseconds, where we can readily see these electron localization oscillations as a function of XUV IR delay. So apparently there, we are able to create electronic coherence. But there are other delays between the two XUV pulses. For example, this delay 4.5 femtoseconds, 7.5, 10.5, where the IR is unable to create electronic coherence. We do not see the electron localization. So that is basically what I now want to explain to you. Actually, here is your summary of the experiment. This is basically the amplitude of the electron localization oscillation that we see as a function of XUV delay. So you clearly see for certain delays, we don't see the electronic coherence. For other delays, we do see it. Okay, so now let me try to explain how we think about this experiment and how we can rationalize this decision. So in principle, the total wave function that we can talk about consists schematically of 4 terms. And what are these 4 terms? I mean, we can either have the ion in the 1s sigma g, a gerade state, or we can have the ion in the 2p sigma u, the ungerade state. And we can have photoelectrons that have odd angular momentum, or we can have photoelectrons that have even angular momentum. Those are in principle the 4 different combinations that we can encounter in our wave function. The problem is, as I already briefly said, that in XUV photoionization, and electronic coherence, of course, means that we need to have a coherent superposition of the gerade and the ungerade ionic states in combination with a photoelectron wave function that cannot distinguish between the two. And so, for example, where the photoelectron wave function is L is odd for both, or is L is even for both. The problem is that the lower 2 of these terms, we cannot form in photoionization. We basically would violate the dipole selection rules. And as a result of that, after the ionization, we only have the 2 terms that are on the first line here, which basically form an entangled system where there is 0 electronic coherence. So the question that we have to ask ourselves is, what can the IR do in order to convert this entanglement into a situation where we have electronic coherence? Now, as we already know from our experiments a number of years ago, the IR can do this in 2 different ways. I mean, the IR can interact with the ion and convert a gerade state into an ungerade state or vice versa. That is one way that we can create electron localization. Or what the IR can do, it can convert a photoelectron with odd angular momentum into a photoelectron with even angular momentum, or vice versa. That we can do the last thing sounds perhaps magical, but please realize it's what we do every day in rapid experiments, in streaking experiments. We always have these kinds of interactions. There's one thing that we need to be aware of in this experiment. I mean, if the IR is responsible for creating the electron localization, then at least one of the paths that we have in our experiment, again, we think of the experiment as an interference experiment, is going to involve IR photons. So that basically means that we have one IR path where that is accompanied by the absorption or emission of an odd number of IR photons, where odd actually means most likely just one, because we keep the IR intensity relatively low. And the other quantum path that we need to consider is where a second XUV photon is absorbed in combination with an even number of IR photons. I call it an even number. Actually, most likely the number is 0 in this case, because we keep the intensity low. Importantly, what this leads to is a situation where the XUV photons that are absorbed in the two paths of our two-pathway interferometer differ in energy by the energy of an odd number of photons. That's basically what we can readily derive here. And therefore, if we want to understand why at certain XUV delays we can induce electronic coherence and at certain other delays we can't, we have to look at our XUV spectrum, and we have to look at how easy it is to find a pair of XUV photons that are separated by the energy of an odd number of IR photons. Okay, and that is basically what this diagram here gives us. So here I'm showing you the XUV spectrum for different delays between the XUV pulses. 0 delay, half an IR period, full IR period, 3 halves, 2 IR periods. And what I'm showing, or what I'm comparing, is basically the XUV spectrum that we get with the XUV spectrum that is upshifted or downshifted. In this case, it's upshifted by the energy of 1 IR photon. And this diagram now explains what we see in our experiment. So first of all, let's look here when the time delay between the two XUV attosecond pulses is 0. In this case, the attosecond pulse spectrum is a continuum, right? And I will have absolutely no difficulty at all to find two photons that are separated by the energy of 1 IR photon. Basically everywhere within the XUV spectrum, I can find these photons. Similarly, if the delay between the two XUV pulses is 1 IR period, or basically a multiple IR periods, then if I pick a photon somewhere within my spectrum, I can be assured that I'm also going to be able to find an XUV photon that is upshifted or downshifted by the energy of 1 IR photon. So that is why in these cases, I can readily see the electronic coherence in my experiment. But now look at the intermediate cases when the delay between the two XUV pulses is a half integer number of IR periods. That basically means that if I pick a photon for my one pathway, for example, I pick a photon on the black curve, then basically I have a lot of difficulty finding a photon on the red curve. I basically have a lot of difficulty finding the photon that I need in order to build my interference experiment. And that is why at these time delays, the IR laser has a lot of difficulty converting the entanglement that we have in the initial wave function into electronic coherence. This is basically the explanation that we have for the experiment. Okay, that brings me to the summary of my talk. So I hope that I've convinced you by both of these experiments that the design of attosecond experiments requires careful consideration of the possible role of ion photoelectron entanglement. We've seen extensively, of course, that we can influence this entanglement by the properties of the XUV pulse. We can tune the attosecond pulse to sequences of interest. What we're going to do in future work is basically look at entanglement of the photoelectron with other degrees of freedom, in particular also internal degrees of freedom of molecules. That should be very interesting to do. And again, I repeat the conclusion from the other night, that I think that this work shows that there's a very interesting link that is emerging between our research field of attosecond science and the field of quantum information. At the very least, we can learn a lot from quantum information. Let me thank again the people who were responsible for this work. So Lisa Marie Kool and Tobias Witting, somehow lost his last name, both did the experiments in the laboratory. And I also want to point out a very nice collaboration that we have with Fernando Martin on the second experiment that I showed you. I mean, there the analysis is still a little bit ongoing, but soon when we're going to write the paper, it's going to be a very nice combination of the experiments that I showed you today and simulations that Fernando and his team have performed and have more or less completed. Yeah, and with that, I thank you for your attention.
So, okay, time for questions. Okay.
Thank you, Mark. Very nice. Here on the one that is on your computer, why do you see delta V equal 2 in the top? You see in the top, yeah, this one, you don't see delta V equal 1, but you see equal 2, it seems to me very well. You have a coherence between 0 and 2, and why? Mm-hmm.
Okay.
If you make such a picture for delta V is 2, then you basically find that at the moment where there's strong entanglement with delta V is 1, there's no entanglement at all for delta V is 2, simply because the energy is twice.
Yeah. And then kind of for the picture about the electronic coherence that oscillates, my impression would be that minima or maxima, you should probe something for the coherence. You seem to care only about the maxima in the amplitude. You had this picture of the oscillation of your signal. Yeah, the one before. Yeah, this one. So
what we're plotting here at the moment is basically the amplitude of the asymmetry oscillation that we see. We fit these for every delay. This is basically the amplitude that we're monitoring here as a function of delay. And of course, what we're currently doing together with Atto is to link this, to connect this to the time-dependent entanglement. That's the work of the mind.
Okay, so we have time for just one short question. Is there any question, Father? If not, then okay, and now we will jump to the Oren Cohen talk. So the talks which was in the program will be after the lunch. So now Oren Cohen will talk about high harmonic generation driven by.
Yes. Well, I want to thank Carla for inviting me and organizing this the wonderful meeting. I enjoyed very much. I think we need to go back. So I will talk about high harmonic generation. And in the past years, we have, we drive a high harmonic generation with a laser pulse. Yes, it doesn't work, right? Oh, no. And we've been manipulating. Previous, at the beginning. We've been manipulating the process of high harmonic generation using multiple beams, as shown, for example, with the bicircular field to generate circularly polarized light and many other things. But now we want to add a new degrees of freedom, and this is the quantum noise of the system. So we explore high harmonic generation driven by quantum light. This light is now described by the density matrix, and we can have, this is a coherent light, so we have the noise, but we can also have squeezing. So in this case, for example, this is a phase squeezing. So the amplitude is very noisy, but the phase is well determined. We can also have the cases where the amplitude is squeezed, but then there is very large uncertainty with the phase. And we can also explore generation of high harmonics with a squeezed vacuum. So this is a vacuum. The expectation value is 0 of the field, but it is squeezed in some region. And this raises some questions. So for example, we know and love the drift state model. The electron do this trajectory, right? Under the influence of the force. But for example, when we have a squeezed vacuum, the expectation values of the electric and magnetic fields are zero. So what is the force? What is the electron motion? And what is the emission in this case? So I'll try to address these questions. This work is really done by a wonderful trio, the three students. Matan Evan-Tsur is my PhD student. Alexei Gorlach is PhD student of my colleague Ido Kaminer. And Michael is a student of both of us. And we also collaborate with Michael Kruger, who is also here. And in fact, okay, this is the authors that did the work presented here, but now we collaborate also with my colleague, former student Pavel Sidorenko, and also with Misha and Olga and others. Okay, let's move on. And we also heard, okay, there is now the field quantum optics in stream nonlinear optics and HAG, but I think it's time to also consider generation of it with quantum driving fields. And the reason is that quantum fields becomes bright. So this would be the first topic or this is the outline of the first topic I want to cover. Then I'll move to the formalism that we use and show how we, for example, calculate the spectrum of HAG. Then move to exploring the electronic motion, the attosecond electronic motion of the electrons driven by squeezed vacuum and squeezed coherent light. And then in the last section, I'll talk about the generation of squeezed high harmonics. So let's start with, okay, really, we think that this is the right time to explore it, and we do it both in theory and in experiment, because following the works of Maria Chekova, who demonstrated that BSV light, bright squeezed vacuum, is already have enough intensity to drive nonlinear processes and really show even enhancement of second and up to fourth harmonic. And in the recent experiment with Peter Romeloff, they also demonstrated the photon statistics of ATI and showed that it has this exponential tail and not the Poisson that is characteristic of the coherent light. And again, so ATI, so BSV already drive multi-photon ionization, in this case from a nanotube. So this is why we think, okay, quantum light is entering the regime of strong field physics, and we explore HAG. So this leads me to the first topic, which is the formalism. And the first thing to do is really to think about HAG. Still, first of all, thinking about just a laser field, but in the context of quantum optics. So basically, we follow the same tricks and approximations that Maciek described in the tutorial. For example, we have start with a single mode and an envelope, and just do the same TDSC and end up with a semi-classical dipole moment that describes the process and leads to, okay, to do the algebra, etc. But it's the same thing that we know, that we have the spectrum is proportional to the square of the square root of the square amplitude square of the semi-classical dipole moments. And now our trick is to describe the quantum light through the matrix, the density matrix. And the way we do it, we use you remember in the answer of Maciek, he described many quasi-probabilities. One of them is the generalized Glauber representation, and actually the specific one, which is positive. And this one, the positive generalized Glauber representation, really has the properties of a probability distribution. It is continuous, it is always positive, and it can also describe any quantum light in the basis of coherent states, alpha and beta. So this is something very useful for us. And once we do it and just do the algebra, we get that the spectrum is really a superposition or integration over the semi-classical dipole moments of alpha and beta. And then we have to integrate according to the distribution of each quantum light. So the Glauber representation, the P Glauber representation, this can be of coherent light. So we have the Gaussian of the shifted, we can have thermal light or squeezed vacuum where it is squeezed in one direction and then extended in the other direction. So we can plug and do the calculation, and then we get the spectrum. So all these spectrums are calculated to the same, with the same averaged intensity. It's just shifted for us to see. So this is the coherent state and thermal state and the BSV. As we can see, we generate, the cutoff is extended, but this has to do with the fact that, for example, BSV has much more fluctuation, and because of the fluctuation, there is a tail of high intensity, and of course, because HAG is a very high nonlinear process, it leads to this generation, but don't take it into, don't consider it as a method to generate very high harmonics, because it's like a nuclear fusion. We invest a lot of energy just to generate the BSV, okay, and then get 1%, etc., or even less. So it's not the efficient way to get to very high order harmonics, but it's still interesting feature. Okay, so now I want to maybe move to explore the electronic motion of an electron that is driven by BSV in order to understand the features. And we start with electronic dynamics in quantum light, and I'll start with free electrons. Okay. So free electrons, we start in just like an initial Gaussian shape, and we so the light matter wave function at the initial can be the initial Gaussian coupled to just vacuum or coherent state, or bright squeeze vacuum. This is the operator that shifts from the vacuum to make it bright. Okay, and we integrate this equation, then take the partial trace to see and observe just the electronic state. And then we can look at the electronic density. Okay. So of course, if we just do it with the vacuum, we get the dispersion, the broadening of the Gaussian, as we expect. If we have coupling to coherent state, then what the electron does, it of course oscillates, and this oscillation gives rise to the pondermotive potential, the average kinetic energy. What happens when we drive it to a bright squeeze vacuum? In this case, the center of the electron is stationary, of course, shown here, but the wave packet is not just broadening. In addition to the broadening, it also has these oscillations, as shown here. Okay, so what we see here is in green and black is the Gaussian broadening to just vacuum, and if it's also interact with the BSV, there is these oscillations. And this is all summarized here. And now we ask, okay, what is the kinetic energy of these oscillations? This would be the conformative potential of the electron under this BSV. It's actually the same kinetic energy. Just like the electron that oscillates in the electric field that shifts here, that it oscillates, the kinetic energy is the same. Now, another thing, we can have different actually trajectory. What I plotted here, these oscillations, is when the electron starts the movement ionized here at the peak of the amplitude. But for example, if it is here, then the trajectory would look like this. And now let's call this closed trajectory, because it comes back to its, like the vacuum, it's vacuum motion. It goes up and down. And this type of trajectories, they just, we call it open trajectories. And we can classify according to the time that the electrons start the motion or release to the continuum, if we think about it in context of HEG, release to the continuum, we will have either closed trajectories or open trajectories. So this is the trajectories we know and love when we have the coherent state. And so we have in solid line, the trajectories that gives rise to HEG, and those that gives rise to, for example, ATI. And for example, those, the source of HEG is really ionization in the first quarter of the cycle. The same thing actually happens here. We have closed trajectories due to ionization in the first quarter of the cycle. That is when the light either is ionized from here, this region. And open trajectory, if it is ionized here in the other quarter trajectory. And moreover, we claim that the HEG that we saw in the driven of BSV are due to this closed trajectory, when the wave packet of the electron really oscillates and comes back. And one indication that we see is really when we think about this electronic motion, I mean, we can write it as a sum over the electronic motions driven by the relevant coherent states. So what is written here is that the electronic, the electron, this is only of the electron, its motion is due to this is also only the electron, and its integration over, and alpha is the parameter. So we integrate over all the relevant fields that drive this electron. And these fields is really some E alpha, which is the center, and different E vac. According E vac is the noise, if you like. And what we see is that those fields that contribute to those trajectories are the same fields that, if we think about this in terms of each coherent motion due to coherent driver, is those that gives the closed trajectory. And the reason is that even though we have many fields here, they are all locked. They have the same phase. Okay, so they have the same phase. So this is why there is the closed trajectory in the first quarter, the open trajectory in the other quarter. They have the same phase, but not the same, necessarily the same sign. It can be positive or negative, and therefore we can have ionization to both directions. But the phase is the same, and therefore we have this, I find it really beautiful. I will not open a poll now about how classical electronic motion under BSV, but I really think, okay, this is, of course, trajectory of the width of the wave packet, but it is still as a classical signature of trajectories. Okay. We also explore it now, the electron motion of a bound electron driven by BSV. Again, using the same thing, just the initial state is now having the bound potential. And we indeed see that the ionization is symmetric. And we can also see that there are ionization and there is flux outward and inward all the time. And we can calculate this burst of ionization and the recombination of electron states. And we see also that it is locked with the oscillating of the driver. So the next thing that I want to do is to move to squeezed coherent light. And squeezed coherent light, I mean, okay, we start with, we mixed really. Think about combining a coherent state, a coherent light, a laser light, with some BSV. And this BSV can be 1%. This is what we explore. So it is really, it's relatively weak. And by changing the relative phase between the laser light and the SPDC, the BSV light, then we can have either phase coherent or amplitude coherent and anything in between. So this is what we shall explore now. And the way to explore it is now that we have really weak squeezing, then we can use the strong field approximation. Because we still think about, okay, both the electron motion is still something which is similar to what we know in laser-driven HAG. So again, we have this descriptions of the density matrix of the light, and then this leads us to writing of the dipole moment. The electrons driven by either coherent light alpha and beta, but doing the strong field approximation in which we take into account only transitions of bound and continuum, then we end up with a much simpler formula for the dipole moment. And here we have it's integration, but in this case only on alpha. We have here integrations over all the beta, so we call it P of alpha, but it is not the P Glauber P representation, P Glauber representation of alpha. It is just the integral over all the beta, and then this is the semi-classical moment. So this is already very simple, and we can calculate it. I mean, either TDSC or directly SFA, and get the results. Okay. So, for example, we can look how the motion of the center of the attosecond pulses, and we see that it indeed shifts with respect to the relative phase between the BSV and the coherent driver So for example, this is amplitude squeezing, and this is phase squeezing, and in between we have just the coherent case. And this is again just the shift. Okay, to see more about the channels, etc., we really do the SFA and solve the SFA. So this is the case of the Levenstein model, in which we, of course, do the extremum and solve with respect to the momentum, the ionization time, the recombination time. And now, when we also have driving light, we have another parameter, because we have to, okay, this is the expectation, the dipole moment, as I wrote before, and now more explicitly, but we have also to integrate over the different coherent light parameter. And this means that when we look for a specific channel, we also need to integrate the action, or to find the extremum of the action with respect to alpha. Okay, so this is additional when we think about channels, ionization, recombination, given momentum, given harmonic specific, and also given a specific coherent light, a dominant coherent light. Okay, and in this case, we can now really find the electron trajectories. And for example, here we plotted the recombination time as a function of harmonic order. In green, we have the coherent state. So we have the short trajectory and the long trajectory, and they coalesce, of course, in the cutoff, but we have the shift. In purple, this is the short and long trajectories in phase coherent, and amplitude coherent it is in blue. So again, we have the electron motion depends on the noise. And we also can calculate really the trajectories. So this is the space as a function of time. When it is comes back, and we can see these shifts. And we ask ourselves, okay, what is the source? What is the source of this changing in the manipulations? And this we can find when we really look at the equations, when we do the extremums to the respective variables. And then this gives us a way to do manipulations of the algebra and go back to the action. And in the action now, we identify that there is additional term. So this is like additional force term. And what is this force term? Where does it come from? It actually, think about this as we have a wave that propagates through some random media. This is the noise, but this noise is structured. There is correlation. And when a wave propagates through some structured noise, it follows it. Okay, it behaves, it acts. The structured noise is like an effective force. This is known in statistical physics, for example. So this is the same source that we have now, and this is additional force, effective force, that manipulates the electronic motion and the attosecond emission. The last topic is now squeezed high harmonics. So in this case, again, now we want to also think about the emission. So we have in the density matrix, both the electron and the wave. And like Maciek described, okay, we have now the light is a product of all the harmonics. So we have the pump, and all the harmonics is really, we think about it as proportional to the semi-classical the semi-classical dipole moment. So this is what we have, and yeah, and we don't take into account any entanglement. We write it as this, as such a product. But within this case, we can now have, we can now plug in our representation for a quantum light. So this is what we do. And then we have the light matter density matrix under these approximations, and we can look what is emitted and look at the Maciek mentioned the semi-function Q, which really describes some of the photon statistics properties. So what we find out that the squeezing of the harmonics, the n omega, has two terms when we do the algebra. One that has to do with the medium. So this is like a Jacobian of different, how one dipole moments depends on the coherent fields that drives it, etc. And one that depends on the driving field. Okay, so we have a material response and the driving field. And for example, we get that the harmonics can be indeed squeezed, but squeezed up to some limit. At the beginning, this here is the squeezing, or the, I would say, the uncertainty of the minimum quadrature of one of the harmonics. And this is the squeezing parameter of the driver. So when we start to squeeze the driver, indeed, all the harmonics become squeezed, the different colors of different harmonics. So all of them become squeezed, but then because HAG is a non-instantaneous process, it feels also different quadratures and the noise coming from different places. At some point, really, we cannot increase the squeezing, and it goes up, and it really goes up and become thermal squeezing. Thermal squeezing meaning that the uncertainty is really beyond of just the circle, okay? There is no less uncertainty than just the ordinary circle of the coherent line. So in this method, when we just think about HAG from isotropic media, this is how it goes. Okay, so this leads me to the summary. I presented that HAG emission is sensitive to the photon statistics of the driving light, and how the photon statistics modify the electronic trajectory. This is through the effective photon statistics force, which is really due to the structure of the noise. And we also explore squeezed pump, how it leads to squeezed harmonics. And okay, this is a list of some of our ongoing projects. We work, of course, towards experimental investigation of these phenomena. And okay, there are also some other things. Thank you. Yes, go ahead. Yeah, yeah. Up. Yes. Yes. Absolutely. The Fock state, indeed, we have also calculated the Fock state. It leads to the same cutoff. I would say, yes, absolutely. You are right that within the process that is described of high harmonic generation driven by one, okay, I call it one laser field. We don't mix, etc. We don't do some tailoring, smart things. This is what we get, that it is really has to do with the photon statistics and not some high order correlations, etc. And I would add more. I mean, I showed that the ponderomotive potential of the electron, the free electron driven by BSV and laser light is the same. We actually know it's the same for whatever quantum light, as long as you describe it as the intensity and not the field. Okay, if you think about it as the average intensity, then the average kinetic energy of the electron is the same. And we actually derived analytically. I did and showed it for. Yeah. I fully agree. Now, this is not the end of the day. I'm convinced that there will be quantum features, but not in this first world.
For the thing, I also like the direction it's going to and it's more also a comment on this question. I really read it. It's really depending on the I would say that why because of you have this long tails in your distribution, and that's why you don't have really want this low expansion of the couple, but still what you mentioned other observers, they might have said about the spectra, also from the battle session, spectra. What's your structure noise, right? Is your focal point hang on local?
It is, yes, no. Yeah, temporal.
If you use this standard high harmonic generation with the non-quantum light, then you have some quantum orbits. And I think that when you add a quantum to this light, then you will just slightly modify these orbits. So if you can combine this classical and quantum light, so just add the quantum with a small percentage and look how the quantum orbits are modified. And then you will follow just the slow change of the quantum, from the quantum orbits to something which you obtain with the quantum light. And then you can just continuously look what's happening, because here it's a drastic change of the cutoff.
Maybe what you suggest is to look for.
Right, the second part of the talk.
Yes, I think what you suggest is to look for a completely coherent light that gives rise to the same trajectories like here.
When you have this.
Like here, right?
Yeah.
I don't know, because I used to think that in HAG, you have the coalesce between the short and long trajectory in the cutoff. But maybe you can find such a thing.
Yeah, practically there are more. It's not only these one and short, but there are some classification of the orbits, and then some of them will be changed, some more, something less. So, but just if you have continuous way to introducing this parameter alpha and everything, then you will see that how this change. But
yes, I guess once a trajectory is determined, you can find the force.
Okay.
To
but it is enough time approximation to the fourth report. But okay, so thank you very much. And we are closed with thank you to the speakers. Okay, now lunch break.